You know, the story of our world, the Cenozoic Era, isn't just some dusty chapter in a geology textbook. No way. It's a 66 million year epic. We're talking destruction, complete reinvention, and just wild climatic chaos. It's really the story of how our planet came back from the brink to create the world we live in right now. So let's dive into the tipping points that got us here. And it all kicked off with an ending, a really, really big one. The Cretaceous-Paleogene extinction event. An asteroid hits, and it's so catastrophic that it wipes out over 75% of all species on Earth. And yeah, that includes all the non-avian dinosaurs. The slate was wiped completely clean. The age of reptiles? Over. And the age of mammals was just about to begin. So that's the big question, right? What happens when you hit the reset button on a global scale? With all the titans of the old world gone, who or what is going to rise up and take their place? Well, the answer to that would be written over millions of years of crazy heat and bone-chilling cold, shaping everything that was to come. Okay, so in this silent, empty world that was left behind, evolution just got to work, and at a pace that is absolutely breathtaking. This is the story of the survivors and how they basically laid the groundwork for everything we know today and what amounts to a geological blink of an eye. The thing that's so wild here is just the sheer speed of the recovery. I mean, it's almost instantaneous. Just 100,000 years after the impact, the number of different mammal species doubles. 300,000 years in, the biggest mammals are 3 times larger. And by the 1 million year mark, you've got specialized carnivores and herbivores, a whole new food web, even new high-protein plants to fuel them. Life didn't just creep back, it exploded. So here's the crucial point. This wasn't just about surviving, it was about opportunity. The dinosaurs were gone. They left this planet-sized for rent sign up. So our ancestors, these small kind of shrew-like mammals, and the ancestors of modern birds, they stepped up. They basically became the new landlords of Earth. And right in that mix, about 63 million years ago, was this little creature called Purgatorius, the well, you get the picture, the common ancestor of every single primate, including us. But this new world, well, it was about to get unbelievably hot. About 10 million years after the asteroid, Earth went through a global heat wave so intense, it's actually a pretty scary warning for our own time. It's called the Paleocene-Eocene Thermal Maximum, or PETM for short. And you've got to understand, this was the most extreme, the most rapid warming event of the last 66 million years. It's really our best comparison for understanding what happens when you dump a massive amount of carbon into the atmosphere really, really fast. It was like a true planetary fever. And how high did the fever spike? A global temperature increase of between 5 and 8 degrees Celsius. Let that sink in for a second. Right now, we are desperately trying to keep modern warming below 1.5 degrees. This was a whole different ballgame. And the cause? This. Over 2,000 gigatons of carbon got pumped into the atmosphere in what was basically a geological instant. We're not totally sure if it was volcanoes or melting methane from the seafloor, but the effect was the same. A supercharged greenhouse effect that just sent the planet's thermostat haywire. The fallout from this was global. The deep oceans turned acidic, which dissolved the shells of tiny organisms on the seafloor, causing a mass extinction down there. Up at the poles, sea surface temperatures hit 20 degrees Celsius. I mean, you could have gone for a warm swim off the coast of Antarctica. And on land, mammals started migrating across newly ice-free land bridges. And some animals even shrank in size, a thing called dwarfing, probably as a way to handle the intense heat. So after the fever of the PETM finally broke, the planet's climate started a totally new journey. This time, it was a long, slow slide into the cold. Let's take a look at how the Earth basically put itself in the freezer. Now, a planet doesn't just cool down for no reason. This massive shift from a hot greenhouse world to a cold icehouse world was pushed along by 2 gigantic tectonic events that completely re-engineered the planet's entire climate system. First up, India slammed into Asia. It was this super slow-motion collision that forced up the Himalayas and the Tibetan Plateau. As these new mountains rose up, they exposed trillions of tons of fresh rock. And this rock, through chemical weathering, acts like a giant natural CO2 sponge, just pulling carbon dioxide out of the air and locking it away. So the world's biggest mountain range became the world's biggest thermostat. The second event happened down in the oceans. It led to the creation of the single most powerful, most important current on Earth, the Antarctic Circumpolar Current. And this one feature would literally change the face of the planet. So as the continents drifted, South America and Australia pulled away from Antarctica. This opened up two huge marine gateways. Suddenly, water could flow all the way around the southern continent. This created the Antarctic Circumpolar Current, which is basically a giant moat of churning cold water that cut Antarctica off from all the warmer waters to the north. It put the continent in a planetary refrigerator, sent it into a deep freeze, and that's how we got the massive ice sheets we have today, and our current icehouse world. So, this new, cooler, drier world created a whole new set of challenges. But with new challenges come new evolutionary opportunities, and these are the ones that would forge the modern world as we know it. With less CO2 in the air and a cooler climate, those lush, globe-spanning forests started to shrink, and in their place, a totally revolutionary new habitat spread across the continents: grasslands. This savannification, as it's called, created a brand new world with a brand new menu, and that would drive the evolution of a whole new kind of animal. Here's the thing about eating grass. It's really tough on your teeth. It's gritty, it's abrasive. So the animals living in the forests, the browsers, they had teeth made for soft leaves. But the new grazers out on the plains, like the ancestors of horses, they evolved these incredibly high-crowned teeth that could handle the wear and tear. It was basically an evolutionary arms race between the tough grasses and the teeth of the animals that ate them. Then, around 3 million years ago, one last big geological change had world-altering consequences. The Isthmus of Panama rose up, connecting North and South America. And this did three incredible things. One, it intensified the Gulf Stream, which delivered more warmth to Europe. But two, here's the paradox. All that extra moisture fell as snow in the far north, which helped kickstart the Northern Hemisphere ice ages. And three, it created a land bridge, sparking one of the biggest animal migrations in Earth's history as creatures moved between the two continents. And this brings us to the final chapter, the most recent past, where a brand new kind of climate instability would forge a brand new kind of animal, us. Yep, this is our origin story. For the last 2.5 million years, our planet's climate has been on a roller coaster. And it's all paced by these subtle, predictable wobbles in Earth's orbit and tilt. They're called Milankovitch cycles, and they are basically the pacemaker of the ice ages, constantly pushing the world into and out of deep freezes, creating a world that is always, always changing. And it was in this world of constant churning change that our own family was forged. I mean, look at this. From Australopithecus in a warmer period, to Homo erectus right when the ice ages kicked off, to our own species, Homo sapiens, emerging during a time of extreme climate swings. This is the whole idea behind the variability selection hypothesis, that our species isn't a product of any one climate, but a product of change itself. And that is the absolute key takeaway. The things that make us most human, our big brains, our knack for tool use, our incredible dietary flexibility, these are not adaptations to one specific environment. They are adaptations to instability itself. We are, in a very real sense, the children of climate change. Which brings us to one last really critical question. This whole 66 million year story shows a planet of tipping points and massive transformations. Our species is a direct product of that volatility, but the instability we are creating right now is happening at a speed that makes even the PTM look slow. So the question is, our species was forged by climate instability, but is our famous adaptability enough to save us from ourselves?